Welcome to the Thevenin and Norton Equivalence Circuits Laboratory using the myDAQ breadboard in conjunction with the LabVIEW software. Objective, of course, of this laboratory is to determine the Thevenin and Norton equivalence of the given circuit in Figure 1 and validate the maximum power transfer theorem. The equivalent circuits are to be determined through measurements taken of the given circuit using the myDAQ. And how we're going to start the procedure for determining this, first thing we shall do is take each one of the resistors intended to be used in the initial circuits shown in Figure 1, and we're going to read the load resistance values to validate them. So, as an example, we're going to take each one of the probes which extend from the myDAQ, red being the positive, black being the negative, place them on either end of each one of the resistors, open up the digital multimeter, select ohmmeter, auto, and read the respective resistance values and record them. Having recorded each one of the load resistance values for resistor 1, 2, 3, 4, and the initial load resistor of 5.6 kiloohms, we're then going to determine the voltage drops across each one of these load resistors. In order to do that, we're going to put a 2-volt voltage source across the circuit and wire the circuit as shown in Figure 2. This is the myDAQ breadboard shown in Figure 2. Notice the output power extends from the output port A0 and the ground from A ground. Brown wire being the ground wire, white wire being the power wire. These strips run vertically, so all the ports vertically along the red line on the left-hand side are all the high side of the input power, in other words, plus 2 volts. Whereas all the ports along the blue line that extends vertically is the ground. Notice the yellow wire extends from the high side, which would be 2 volts, to the ports which run horizontally. This is the input node for both the load resistor number 1 and load resistor number 2. Notice in Figure 1 that they share a common inlet node, just as they do on the breadboard. Load resistor 3, of course, extends from the outlet node of load resistor 1 to ground. Notice as I'm moving the cursor across, you can see the orange wire which extends from the outlet node of resistor 3 to ground, just as shown in Figure 1. The load resistor 2 also extends to ground. Notice it shares a common outlet node with resistor 3, just as you see in Figure 1. Load resistor 4 extends from the outlet node of load resistor 1, just as shown in Figure 1. Notice there's a jumper. Again, the ports that you see to the left of both the ground and the power strips on the left-hand side of the breadboard are a common node horizontally. So this orange jumper wire that you see connects the outlet end of load resistor 1 to the inlet node of resistor 4. Once again, notice that on the breadboard, the outlet node of resistor 4 is connected to the inlet node of the load resistance, and the outlet end of the load resistance is jumpered via the brown wire shown on the bottom of Figure 2 back to ground. the yellow wires that the long yellow wires that you see in figure 2 connect each end of the load resistance to the input ports on the breadboard. That would be IO0 negative, IO0 plus. And what we're going to do is construct a VI, a LabVIEW VI, which is not only going to we're not only going to provide an output voltage to send to the breadboard, but we'll also take feedback from the breadboard, as shown in figure 3. We're going to open a myDAQ assistant, an input controller, rename it input voltage, and we'll assign it 2 volts. That will send out the power. This particular myDAQ assistant will send power out to the myDAQ breadboard. The voltage drop readings across the load resistance that you saw in figure 2 with the 2 longer yellow wires will come back to the LabVIEW software via the myDAQ assistant, as shown in the lower half of the block diagram in figure 3. As an example how this is done, we're going to create a numeric indicator. As well as myDAQ assistant. This particular LabVIEW, the computer I'm using, does not have the myDAQ assistant software set up on it. The computer that I normally use crashed, so you'll have to bear with me. But imagine that we're running a wire directly from the numeric control to the myDAQ assistant. And then from that point, what we'll do is double click the myDAQ assistant. Double clicking the myDAQ assistant, we'll select acquire signals, analog output, or analog output voltage, IO0 or IO0, finish and OK. That will be our outlet. That'll be our outlet signal to the myDAQ assistant. In essence, the voltage source. Similarly, we'll open a second myDAQ assistant, output, and we'll create a numeric indicator. And what I told you, I actually got it reversed. First myDAQ assistant, that'll be our output indicator. We're going to double click on the myDAQ assistant, the initial myDAQ assistant, acquire signals, analog output, voltage, A00, OK and finish. That will be our outlet to the myDAQ breadboard. Our input, once again, input, myDAQ assistant, and then we'll wire the indicator to the input. This is where we'll receive our voltage readings in from the circuit that we've constructed. Heading back to the circuit, this is what the figure 3 indicates what the figure should look like when you're finished. Now that we've read all the load resistance, read and recorded all the load resistances for each one of the respective resistors. Now we want to go ahead and read the voltage drops across each one of these resistors. How we're going to accomplish this is as shown in figure 2. We're going to take the yellow wires, just as we've read across the load resistance for the load resistor shown, you notice again the input wires to the bed out to the LabVIEW software, headed out to both IO0 negative and IO0 plus, surround the load resistance. We're going to take a reading here after we hit run in our LabVIEW software, and we'll repeat that for each resistor shown and record the values. Once we've accomplished this, we've got most of the data that we're looking for. But of course, what we want to do is validate what we've done in our pre-laboratory assignment, which is to determine Thevenin voltage, the Thevenin resistance, and the short circuit current. Short circuit current is going to be a little, we will have to calculate based off of values that we derive off of that circuit branch, as a forewarning. Taking the open circuit voltage, the open circuit voltage, which should be equivalent to your Thevenin voltage, we're going to remove the load resistor from the circuit, as shown in figure 4, maintaining the voltage source, and we'll take the reading across these two ports. This will be our Thevenin voltage. As an example, notice that the circuit, as shown in figure 2, is completely intact with the exception of the load resistance has been removed. The yellow wires are still headed to the output port. Once we remove the load resistor, we're simply going to hit run again and take the reading off our indicator in our VI. This will give us our Thevenin voltage, which should be equivalent to what we calculated in our pre-laboratory, approximately 1 volt. Having accomplished that, now we want to calculate our short circuit current. In order to calculate the short circuit current, referencing figure 5, we're going to determine the voltage drop across the load resistance 4 and then divide that by the measured value that we just determined for resistor number 4. So once again, referencing figure 2, the two yellow wires shown delivering the output signal to both ports AI0 and AI0 plus. We're going to relocate those from the inlet and outlet nodes around the load resistance. We're going to relocate them to the inlet and outlet nodes of resistor 4. We're going to simply run a wire from the outlet node of resistor 4 to ground. The voltage reading we take across resistor 4 doing this is going to be the voltage drop that we effectively divide by the measured value for resistor 4. This is going to supply it. This will provide us with our short circuit voltage to compare against what we determined in our pre-laboratory report. This value should be approximately 0.256 milliamps based on the circuit provided in figure 1. Finally, we're going to determine the Thevenin resistance as measured for the circuit provided in figure 1. In order to do this, once again we're going to remove the load resistance and we're going to short circuit the supplied power. Notice where I put the cursor. This is where the power has been short-circuited. We've effectively connected the inlet port for power along the red strip. We've jumpered it to ground. Ground being where I'm running my cursor across. Notice the load resistance has been taken out where I'm running my cursor vertically, or horizontally rather. And I place my two probes once again, my red, my high probe, and my negative probe, across the positive end across the outlet end of resistor 4, and the negative probe effectively to ground. Taking our digital multimeter once again, we select ohms, auto, and read the load resistance, or read the resistance. This resistance is effectively our Thevenin resistance, and it should be comparable to the Thevenin resistance that we calculated in the pre-laboratory. For this particular circuit, it should be 3.9 kiloohms. Now that we've completed this portion of the laboratory, it's time to begin validating the maximum power transfer theorem. In order to do this, we're going to select an additional 10 load resistors, varying anywhere between 0 ohms and 5.5 ohms, or 5.5 kiloohms. We'll record, just as we did earlier with regards to resistor 1, 2, 3, 4 in the initial load resistance, we're going to use our digital multimeter once again to measure the load resistance, or measure the resistance across the actual measured resistance for each one of these resistors that we've selected. Referencing figure 2, each one of these resistors will then be placed into the circuit. The voltage, the 2-volt power supply voltage, the DC voltage, will be applied to each one of these load resistors, and a measurement will be taken for the voltage drop for each one of these resistors and recorded. Once we've collected all the data, now it's time to analyze the data that we've collected. We're going to open a new LabVIEW VI, and we're going to calculate the currents across each one of the resistors, as well as the load resistance, and also the power drops across each one of the resistors. You notice if you notice figure 8, we have the measured load resistance, which we divide into each one of the voltage drops, following my cursor. This will give our calculated current from the values that we measured earlier. Then we're going to want to multiply the current value that we've just determined, times each one of the associated voltage drops to determine our power drop across each one of the resistors. The top diagram is the block diagram that you should be using to manipulate, or I intend on you using to manipulate the values associated with resistor 1, 2, 3, and 4. With regards to the load resistors, the 11 load resistors that we're referring to, the initial load resistor plus the additional 10, looking at the lower block diagram of figure 8, we're going to take the resistor values that we measured with their associated voltage drops, once again dividing the voltage drops by the resistor values to determine our calculated currents, multiplying those currents by the resistors to come up with the power dissipated across the load, and then building a graph from that. graphing the dissipated power across each one of the load resistances versus the actual measured resistance should give us a graphic display which is approximately close to, which would indicate that the maximum power dissipated occurs at a resistor close to the Thevenin resistance that we measured just a few moments ago, which is consistent with the maximum power transfer theorem. Maximum power transfer theorem once again states that the maximum power dissipation occurs when the load resistance is equal to the Thevenin resistance. As an example of the as to how you want to construct your VI to manipulate the data, I'll briefly go over the LabVIEW program that I constructed. Once again, referencing the front panel, I've recorded the theoretical resistances for all the resistors, the measured resistances, and the measured voltage drops that I took in the first portion of the lab, from which I've constructed with arrays load indicators which calculate the current, a simple Ohm's law, dividing the voltage drop measured by the resistance values to determine the current across each resistor, and then multiplying this current times the voltage drop to determine the power. The same is then repeated for each one of the load resistance values. You see the load resistance values in the front panel, the control indicators, with each one of the values entered that we measured. Here you see the theoretical values for each one of the resistors. You see the measured values for each one of the resistors I recorded, and the associated voltage drops that I measured. Referencing the block diagram, you see that the data manipulation is similar to what's shown in the write-up for the laboratory. Once again, simply taking the resistance values that are measured, dividing these resistance values into the voltage drops measured to determine our current, and taking the current values that then we have just determined and multiplying by the voltage drops for each one of the resistors 1, 2, 3, 4, we determine the power, which again is listed on the front panel in the indicators, both for power and current drop. That's the block diagram. You see I'm circling with the cursor now. For each one of the resistance values, the load resistance values have done the same thing. Don't be confused where it says sort 1D array. What I've simply done is I've sorted each one of the arrays that you see that I'm circling with my cursor in the front panel. I just sorted them in ascending order. And I've ensured that all the values that I have when they're sorted, they continue to match, which is consistent if you think about it. Consider this: you would expect that if you get a higher resistance, you should get a lower current flow. But either way, the values that you want to ensure that the values that you've recorded in these indicators, when you sort them, or if you choose to sort them as I have, that they continue to match. Say, for example, the 5.5 theoretical, 5.51 measured, and 0.587 volt drop. If you look down below it where it's been in the sorted values, you'll notice that it remains consistent. It's 5.5, 5.51, 5.87 volts drop. So the sort worked correctly. You want to validate that to make sure that your numbers remain true. You don't make a mistake. Once again, looking at the block diagram to the right, you see the resistance values that are measured across the load. After they're sorted, they're then divided by the voltage drops to come up with the calculated currents. And of course the currents are then indicated in the front panel. As you see here, I'm running the cursor across it now. Each one of the calculated currents across the loads in milliamps. Using this current that we just calculated, we then multiply it, following the block diagram. We then multiply it by the voltage drop across each one of their associated resistors. This will give us the power dissipated across each one of the resistors in question, the load resistors. Now that we've determined and recorded, or I should say calculated, the power dissipated across each one of the load resistors along with the current, now what we'd like to do is to have a graphic analysis of it. So what we're going to do is we're going to build a graph of power versus versus the measured load resistance across each one of the load resistors in question. So, in case you're not aware of where to pull the graph out, we're using an XY graph. Pull out the XY graph, and I'm just going to go ahead and stick it here, and then I'm going to remove it. That was just simply to show you where I got it from. You pull in an XY graph, place it in the front panel, and its associated icon in the block diagram, we're going to wire it to our XY build graph. Our Y input is then going to be the power that we've calculated across each one of the load resistors. And our X-axis, of course, is going to be the measured value for each one of the load resistors. When input into the graph builder and into the graph, you'll get a distribution similar to what you see in the front panel. You notice that the line increases, power dissipation increases up to approximately a value very close to 4, probably very, very close to the 3.9 kilo ohms that we determined in our pre-laboratory for the Thevenin or the Norton equivalent resistance. In short, the values that you calculate in your LabVIEW software should be very similar to what you calculated in pre-laboratory report. Having completed this portion of the lab, again, you should get a graph just as displayed in Figure 9. And recall that the maximum power transfer theorem is defined as the Thevenin resistance squared divided by 4 times the the Thevenin resistance. Let me repeat that. The maximum power transfer is defined. The maximum power occurs at the Thevenin voltage squared divided by 4 times the Thevenin resistance. With that said, additionally, what we're going to do is determine the error for each one of the values the errors we will perform an error analysis using LabVIEW software for the short circuit current, the Thevenin voltage, the Thevenin resistance, and the maximum power transfer to the load resistance. Referencing once again is an example of the sort of block diagram that you're going to build for each one of these error measurements. This in figure 10 happens to be for the short circuit measured. You might recall earlier we measured the short circuit current to be approximately 2.56 milliamps. We're going to we're going to compare that against the calculated value that we received, which should be again very close to 2.56 milliamps. Subtracting the difference from one another, and then dividing by the calculated short circuit current, as shown in the general expression for error that I'm circling with my cursor. Of course, multiplying by 100, the quotient by 100, will give us a percent error. So this is generally what we're going to do for each one of these values. Once again, we're going to calculate the error, perform the error analysis on the short circuit current, just as shown in figure 10. Additionally, for the Thevenin voltage, Thevenin resistance, the maximum power transfer to the load. Moving back to our block diagram, you notice how each one of the values are calculated. Now I haven't thrown them in the front panel. I haven't thrown the values in the front panel yet. But if you look at the Thevenin voltage, we're putting in our measured Thevenin voltage versus our calculated Thevenin voltage. The formulas all are similar. So running through it real quick, the Thevenin voltage measured, taking the difference between that and the calculated value, dividing the difference by the calculated value, multiplying by 100 is going to give us the error in the Thevenin voltage. The power error, recalling once again the equivalent power theorem, just quickly go back to our lab write-up. Maximum power transfer theorem defines that the maximum power occurs at the Thevenin voltage squared times divided by 4 times the Thevenin resistance. With that in mind, we've taken the square of the calculated Thevenin voltage and divided by 4 times the calculated Thevenin resistance. This gives us a theoretical value per the maximum power transfer theorem. Taking the difference between that and the maximum value of power in watts that we actually measured, notice that the value for this icon determines the maximum value of a particular array, and this array that we happen to have connected to this box is the calculated power across each one of the load resistances. So once again, we're taking the maximum power, determined across every one of one particular value, the maximum power dissipated across one particular load resistor, and subtracting it by the calculated maximum power dissipated per the I want to make sure I get it right, give you the right, for the maximum power transfer theorem. I want to make sure I'm clear so I'm not confusing anyone. Again, taking the difference between the two, multiplying by 100 gives us the percent error in our maximum power figure. Similarly, as we ran through in figure 10, the short circuit current measured is then compared against or subtract, or the difference is taken between the short circuit current measured versus the calculated value. The difference is then divided by the short circuit current calculated value multiplied by 100 to give us the percent error for the short circuit current. The same is then done for the Thevenin resistance measured. Thevenin resistance we measured early in the laboratory is then compared against our Thevenin resistance that we calculated in a pre-laboratory report. That difference is then divided by the calculated value for the Thevenin resistance, multiplied by 100, and that provides us with our error. And bearing with me just for a moment, I'm going to pull up the values that I actually determined so we can run through it in LabVIEW and you can see what the results are, so you'll have something to compare it against when you perform the lab. And better yet, what I'll simply just show you what the results file showed. Notice that this is just a printout of the same page that we're looking at, except with the last portion of it filled out. You scroll down toward the end, you'll see the same, and this is again a printout of the same file we're looking at. The entered Thevenin result voltage calculated versus what was measured. I measured 1 volt versus I calculated 1. And then you're going to see the percent error that was calculated. Notice it's nearly 0. I've also entered the short circuit current I calculated versus the short circuit current that I measured, right? Which is in essence a calculated value, because what we did is we took the voltage drop across resistor 4, if you recall, and we divided it by the resistance measured for resistor number 4. That's where this 0.255 milliamp value came from. Again, via the block diagram in LabVIEW, we've calculated the percent error in the short circuit's current. And it's almost negligible, very close to 0. A Thevenin resistance value I calculated at 3.9 kilo ohms. And then you see the Thevenin resistance measured, 4.1 kilo ohms. This introduces an error of about 5%, and there are reasons why this may have occurred, and you might want to include this in your lab report. There's more than just simply resistance in each one of the resistors. There's potentially resistance that runs through the wires in addition to the breadboard that may have introduced some error into that measurement of 4.1 kilo ohms. In addition to that, since we're using probes to measure it, there's human error also involved. If you don't, again, when the measurements are taken, if your hands aren't steady, you may get an erroneous reading, which would result in a 5% difference. Okay, now that we've created our LabVIEW VIs to analyze our data we've used the myDAQ breadboard to measure the values that we were looking for. So performing that, having performed all of that, you're ready to write up your lab report. Once again, just briefly going through the laboratory report, you're going to want to display, as we did in LabVIEW, all the measured resistance values, measured voltage values, calculated current and calculated power values. You're going to include your theoretical analysis performed in the pre-laboratory, right, for comparison purposes against what is actually measured and calculated in LabVIEW. Using the measured resistance values, we're going to compute the theoretical value of the load resistance, which provides the maximum transfer of the load, which should agree with the pre-laboratory, around 3.9 kiloohms. Again, on top of that, we're going to provide a LabVIEW graph that provides a graphic display of where this maximum value actually occurs. And lastly, we're going to calculate the percentage error associated, or provide analysis of the calculated error for each one of the pertinent measurements, that being the short circuit current, the Thevenin voltage, the Thevenin resistance, the maximum power transfer, the load resistance, both calculated and theoretical, and present the error for each one of those measurements, as well as analysis. If there's a difference in your report, account for it. Account for where you think the error might have come from. This concludes the Thevenin and Norton Circuits Laboratory. This should have given you an overview. You should be able to complete the lab. And if there's any questions, please let me know. Have fun. Thanks. Bye.